present unaligned 2D to 3D translation with conditional vector-quantized code diffusion using transformers. Given two 2D images as input, our method generates high-quality 3D samples of complex data that exhibit both varying outer and internal topologies with different material properties and domains. For instance, medical X-rays and CT scans and security baggage screening from airports. In contrast to natural images or common 3D datasets that are purposefully geometrically aligned, real-world imaging rarely shares a common coordinate system and often displays different domains. Moreover, real 3D images can contain diverse topologies where objects can be transformed in different ways. For example, a pair of shoes stored inside a suitcase can be located at any position, occluded, or even squeezed by other denser or less dense objects. All of these challenges difficult the translation of real-world imaging modalities. Our approach approximates a conditional probability distribution of generating a complex 3D image from two 2D input views by parameterizing a discrete diffusion model with a non-constrained transformer. We decompose the task into two stages. First, separately, we encode 2D and 3D data points using vector-quantized autoencoders. Each encoding is quantized by mapping to the closest element in a rich information codebook. Then, the discrete latents are decoded using a convolutional neural network. Our approach eliminates the need for spatially aligned 2D and 3D images. In addition, our model allows the use of an arbitrary number of 2D input views without the requirement of camera priors or changing the network architecture. In the second stage, we perform 2D to 3D translation by modeling the conditional probability distribution in the learned vector-quantized space. The 3D latents are gradually masked out, defined by the Markov chain. The reverse of this diffusion process unmasks the latents using another Markov chain conditional on the 2D latents. We use an unconstrained transformer to parameterize this denoising function using an absorbing diffusion process because of its bidirectional nature. Our approach is geometrically invariant over the 2D latent and provisions 3D image likelihood estimates while also providing faster sampling. To demonstrate the applicability of our proposed approach, we conducted a set of experiments on two datasets, portraying different topologies and domains, including complex volumetric imagery from publicly available chest CT scans and security baggage screening. We evaluate using density and coverage and traditional distortion metrics. Our approach demonstrates a state-of-the-art performance across all datasets compared to three methods, including GAN-based and NERF-based approaches. To summarize, we propose a novel translation approach based on conditional diffusion using transformers, giving state-of-the-art 3D samples conditional on two 2D images from a different domain. We show that translation diffusion in the latent code space not only allows for our model to scale easily to high resolution, but also allows for unaligned inputs, as the attention mechanism is geometrically invariant over the entire 2D latent code space. Our model is shown to give a state-of-the-art density and coverage over competing methods while offering true likelihood estimates.